Now we are live. Okay. Hi everyone. I'm very happy. I'm very proud that Professor Kasabov decided to join us here on this next live. As you may already know by now, this channel is focused about biomathematics, and I was doing research to my next book, and I found by chance the book of Kasabov, Professor Nikola Kasabov, and I was surprised because I saw his talk about his. He gave a short 1 week course, which was very nice to course. At the time, I didn't know about anything about spiking neural networks, and he influenced me to go on. I mean, we tried to collaborate, but I mean, didn't do work very well. But I hope in the future may collaborate a little bit more in intense way. And I just sent him a message on LinkedIn, and he was very kind to reply me. And I invite him, and he was very fast to accept. And I cannot say how proud and how happy I am for him to be here. So thanks, Professor Kasabov, to be here to accept the invitation.
Yeah, thank you. I should say that that's a very timely initiative by my colleague and whom I met years ago, and now I'm very happy to see that his activities, her peers, are worldwide activities, and it's a pioneering work to do to keep the community working together, because in the situation we are separated, and now we are no more separated with disabilities and with these facilities and the pioneering work of some people. So thank you very much for inviting me here, and I'm happy to discuss things and even to open some open questions for the future. I should say that the topic that I would like to talk today and discuss with the audience and take questions and take challenges is called brain-inspired computation with spiking neural networks. Now, first of all, what is the difference between using formulas to calculate numbers, to crunch numbers, and the brain-like computation, brain-inspired computation? Well, the difference is a huge difference. Brain-inspired computation is based on learning, as everything that the brain does is based on learning. We learn from experience. We learn from our genetic code that is working all the time within us. We learn from the environment. We adapt. We change. We embrace data and knowledge together, and that is the difference between calculating, number crunching, and brain-like computation. Brain-inspired computation, indeed, is based on learning. And I have some slides. Maybe we can show some slides.
Yeah, for sure. Be my guest. You can show the slides. Just share the slide. I will show you for everyone. Please.
Yeah, let me say that just a few words before I would like to have more discussions. Can we have the next slide, please? And I should say that brain-inspired computation is very much driven by what we know about how the brain works. And the brain has billions of neurons and trillions of connections that are evolved through evolution. And the brain is learning in a very sophisticated way. We have learning at different levels, as nanoseconds, milliseconds, minutes, hours, many years of evolution. This learning in the brain can be simulated and can be used as inspiration for developing novel methods for computational intelligence. Next slide, please. And here is one example how we learn to recognize an object and to pick up this object. For example, recognizing this cup and picking up the cup, looking and activating different areas of the brain, different clusters one after another, connecting them into a trajectory that after seeing the cup, I can move my hand and pick it up. So this is the knowledge we build through learning, and that is how we process how we live with this environment to capture knowledge, to learn these trajectories of activation in the brain, and these trajectories can be represented in a simulating environment as spatial temporal rules, because here we have both space and time of activities. Next slide, please. And the recent development of artificial neural networks led to the development of the third generation, so-called spiking neural networks, when information is represented not as colors, but as units or spikes at a certain time. So spike is nothing without time of its spiking. So we have the spikes at different spatial areas at certain time, and that makes patterns. These patterns are learned in the brain and can be learned in artificial neural networks like spiking neural networks. Next slide, please. And here we have different types of learning. For example, we have unsupervised learning, where we have, for example, spike time-dependent plasticity, where two neurons learn their connection weights based on the time of spiking. So connections, they learn time in their and their values. So this is different from traditional neural networks or deep neural networks, where time is not learned in the connections. And in our brain, we learn time. And in these spiking neural networks, they learn time of activities. Next slide, please. And the question is, how do we encode external information into spike sequences? There are different ways. They can also be inspired by the human brain, by the retina, that transfers pixels based on their changing of brightness into spikes, or cochlea that actually has neurons that react to certain frequency of the sound, and this frequency activates neurons to emit spikes and to send these spikes further to the auditory cortex. And we can see we have some other methods for learning. For example, supervised learning. Next slide, please. Where we can train spiking neurons to emit a spike at a certain time when certain spatial temporal pattern is presented to the spiking neuron. Next slide, please. And we have some systems that develop as evolving systems when neurons are created, connections are created, rather than we have a fixed structure that is fixed forever. No, I think we can have, with some methods called dynamic evolving spiking neural networks, we can create systems that evolve their structures. Next slide, please. And having these theoretical aspects of spiking neural networks and learning, we can build so-called brain-inspired architectures, and we can have a brain template used to structure the spiking neural network, spiking neurons in a three-dimensional space, and every neuron from this space has certain correspondence to areas of the brain. So we have a brain structure here. Next slide, please. And here, this is one of the such brain-inspired structures is called NewCube. And NewCube is developed to capture some data and to learn connections from the data, so that after learning, we have patterns, as I showed before. We have trajectories that are learned from the data, and the learning is local learning. We change connection weights between two neurons, the time of the, but during this learning, they connect to each other and they make patterns, they make trajectories, they create knowledge. Next slide, please. And here's how they work. The system, the spiky neural network, three-dimensional brain-like, brain-inspired, takes some data, input data, and creates some connections. And these connections are created based on some rules, local rules like spike time-dependent plasticity. But as I said, patterns are created as a result, global patterns through local learning. And these patterns represent certain actions, certain classes, and that could be used for classification, for prediction, for brain data analysis, and not only from brain data analysis, but for some other spatial temporal or temporal data modeling. Next slide, please. To design an application system based on these principles, we have to go through certain phases and certain procedures. For example, analysis of the data, designing the reservoir or the structure, encoding the data, learning this system, etc. And all this is so-called the design procedure that we have to go to design our application. Well, the brain was designed through evolution for many millions of years. Now we can design a system that is brain inspired within few hours, but that is due to the technology. Next slide. And some applications, the applications are, of course, broad applications. And the brain is a universal learning machine. We can learn languages, we can learn actions, we can learn to speak, we can learn to act, we can learn to play soccer or cricket. So it's a universal machine, and we can learn to protect ourselves, to predict events that can hit us, kill us, and that is something that we can also implement in artificial systems. We can train them on audio-visual signals, on speech, on image, on movies. We can train them on biological signals like brain signals, CEG, fMRI. We can train them on multisensory streaming data like seismic data, and I'll show some applications in the next slide. Next slide, please. So here we have trained different spiky neural network systems on different music by composers, and these composers are here. We have Beethoven, Bach, and Vivaldi, and we can see the patterns that are learned are different from different composers, and the patterns are learned through the so-called stereo learning, because in a brain template of a spiky neural network, we can have left and right hemisphere that represent.
Professor Kasabov, because this part caught my attention. No, all the slide caught my attention, but I sorry to stop you because I was I'm reading a book about TensorFlow.js, which is deep learning in JavaScript, and I found a project by Google in which you can play, and the computer will make for you like a drum. You don't have a drum, the computer is your drum. And the computer was pretty good. So is this the same? Do you think that it is able to learn the music? For example, if I want to play Beethoven, for example, but I don't know how to play Beethoven, but I wanna make a beat. I wanna ask the computer to make the beat in the background, like a bass, using Beethoven. Is it composed song? Can you please explain a little better?
Yeah, that is possible too. Can you have the next slide, please? Thank you. So, in terms of vision, we can substitute the current systems that use camera to capture frame by frame information. We can use the so-called dynamic vision sensors, where every pixel is transformed into spikes, so the system can react much faster. Next slide, please. And this could be used for detecting moving objects and very fast moving objects as well. Next slide, please. And the methodology, of course. Next slide, please. So we have series of, we can use it for brain data analysis, for EEG, fMRI. Next one, encoding the data, learning the system, and evaluating the connections and classifying the pattern. Next slide, please. Also, virtual reality, how we work in a virtual reality and how our brain reacts to virtual reality. Do we have sickness, cyber sickness or not, can be also modeled. Next slide, please. Seismic data can be used as a spatial temporal data that is used to build patterns, predictive patterns of earthquakes. And this is one particular application that is currently being developed in collaboration with an international team. Next slide, please. And the future, of course, is taking more information as bio and neuroinformatics is growing areas, and this information can be used to develop new systems. Of course, there are some ethical problems, and I would recommend one website which is called mindthegap.ai that discusses ethical problems. Next slide, please. And the implementations neuromorphic are from simple computers that we have to implement spiking neural networks and brain inspired to neuromorphic platforms. Next slide, please. And neuromorphic platforms, they realize spiking neurons as millions and billions of them within chips and boards. And here we have Spinnaker as an example by Fulber, and we have Giacomo Indiveri and Toby Delbrook and Martin McGinnity from Ulster. Next slide, please. And of course, the future is in this direction, and I have discussed some future directions as human-computer interaction based on common platforms, and in this book. Next slide, please. And this is my group. Thank you. And I'm happy to take some questions as well.
Let me just, let's see here. So, hey guys, you want to remember that you can make questions, can make comments. The live will be available. Professor Kasabov kindly accept to leave his slides after math, so you will be available in the description of the video. Until you guys have some questions, I do have a couple of maybe comments. Because last chapter, I was see my screen. Can you see my screen?
Yeah.
I had one picture that I'll not replicate here just to avoid, because you are finger, so I think this guy can make mess up. Anyway, it's copyright, but this one can use it as a Creative Commons. It's that pic of your picture. I was surprised because you said something like, I was thinking to myself, because there is a movie called the Amelia. It's a science fiction movie, Amelia 2.0. It's a movie that the guy was able to make artificial intelligence. The artificial intelligence was able to replicate his wife. So in the end, he killed the robot because his emotion was too close to his wife. He didn't want to have a robot as artificial intelligence robot as a kind of wife. When you see this model of yours that's called brain-inspired artificial intelligence, it seems to be very close from encoding what is inside the brain. So if I understood properly, you are essentially trying to make a kind of I think here because you're trying to do a reverse engineering. Like you have the brain, you encode the information somehow using spike in neural network, using this kind of technique. You put in the brain of the robot, and the robot is able even to have the knowledge, the experience of the person, and want to talk, to communicate. It seems like you are even closer from the kind of communication that you may have with the computer. I got it right, or there is something wrong here?
You are absolutely right. I think this is the way to go for making robots brain inspired, brain-like, so we can communicate with this robot in a more natural way, and we have them close to the way we learn, close to us in terms of what we do, and we can make them to do things like we do, and that is the future.
Yeah, because I was quite surprised because of that. Because so far, I even though in my brain I can go in the future, you kind of scared me because I thought we were very far away from that. But your book made me think like we are very close because in my brain I was thinking like in the future we may be able to communicate with computer, but it seems that the spike network is making us even closer to that because you'll be able somehow to but for you guys that do not know what is artificial neural network, it's a kind
Just
of technique
yeah,
used
and
for
this is
machine
just
learning.
the tip of the iceberg. So I think there is a long way to go in this direction, and we're happy to just to start some first probably architectures and first experiments. But the future is rich of ideas and development.
But how far do you believe? I'm not talking about precise date, but I'm talking about uh, because on this channel you had two different lives. One by John Takar, he talked about the whole cell. The other one by Alexei Kolondik, he talked about the virtual human. So it seemed for me that your part is a virtual brain. So today you have virtual pancreas, have virtual liver, then you have the virtual human. But now it seems to me that your contribution will be a virtual brain. Can I say that? I mean, the contribution of the bias by the AI.
That is one way to say that, of course. That is one way. Yeah.
Because all the data is very hard to model, but the brain has been quite hard because most of the for the deep learning is like it's very nice, but it's not very brain-like. It's like it's a technique for math,
Exactly.
like you.
Exactly. The brain doesn't learn using the traditional deep learning methods because the brain doesn't have a fixed learning structure. It is self-organizing and it creates new connections based on the data. And the system doesn't have to be restricted in terms of number of layers, number of neurons in layers as the traditional the current deep neural networks. It is self-organizing itself, making pathways, making trajectories based on local learning. And this is deep learning, which is brain-inspired or brain-like deep learning, rather than the deep learning that is the standard one at present.
Yeah, let me just use one note here because I was able to on the beginning of on the beginning of the chapter of your book, the last chapter, which is the I would say the cake, the big stuff is there. As you said yourself, you said there are few concepts you use a lot on your book. I'm trying to say here, deep learning. You said in the deep knowledge. I guess the deep learning is the deep learning artificial network, or that's a kind of deep learning, just the name. I want because you said deep learning, deep knowledge. Do you mean like deep learning? Because the word deep learning is a bit dangerous because you give the idea that deep learning is deep learning, but it's not deep learning, just the name. I mean, it's a huge amount of hidden layers, and then it's not very deep. Like Google Translator. Google Translator is pretty bad to make sense of sentence. If you ask a very complex human-like sentence, Google Translator cannot do it.
In human-inspired deep learning is different from the traditional one. And we can look at the deep learning at different levels of clustering and granulation, starting from two very little neurons, learning to each other, learning connections to each other based on time. But then we have clusters of neurons that connect between each other in a self-organizing way, and they make a deep trajectory. How deep? Well, if you take one neuron, the granulation of one neuron, it will be million neurons deep. But if you take granulation of clusters, it would be 100 clusters deep that are formed in a self-organizing way. So we don't have to specify how deep it is. It just happens.
Okay, so for the guide of the deep learning, keep in mind that the deep learning itself is brain spiral network. they are a kind of deep learning that's more connected to the knowledge, if I understood properly. It's different from the deep learning that you use in deep learning artificial network, more deep in the sense of shallow, the opposite of shallow. Shallow, you just have a small amount of layers. So in the future, we may be using this kind of deep learning that Kasabov is talking about, but it's more and more about like human-like, different from the deep learning, like a huge amount of layer.
Yeah.
It's easy to keep that in mind because people may get a little bit confused because deep learns all around deep learning in the sometimes you
Well,
can.
I think we don't want to speculate with this name, but it is indeed a deep learning in the human brain. And this is indeed a deep learning, and it's the approach that we take as a brain inspired is scalable. We can have a system that has 100 neurons on 100 million neurons, and that defines how deep it is in their structure, self-organized structure. It creates these patterns, and we call it deep learning without actually speculating with the name, and that's a real thing that happens.
And let me just say, it seems to me, I read a book, a very good book by Daniel Kahneman. Daniel Kahneman, he was a Nobel Prize psychologist. He got Nobel Prize in economics, and he published a book recently, which I love the book. I read the book several times. I cannot stop reading the book. I'm using the book about computational thinking because he has the third part of the book is about the decision making. And he talks about models like artificial intelligence, regression. And he makes them, and he talks about something very a little bit scary sometimes because very simple model like regression can beat human in the decision. Because as he says, sometimes you think that you know why you took the decision, but you don't know. But when you make this kind of coding that you said, like I have brain-inspired artificial intelligence, what's the probability that you can make the same kind of human mistake? Because if you go to Google image and you type in Portuguese like black hair, in Portuguese bad hair, you go to black people because you have a kind of prejudice in the society. But Google image was able to also to incorporate these prejudices. It's not just in Brazil. I also saw some research in the United States in which they try to use artificial intelligence to make a judgment, like judger, like a court. And the artificial intelligence was always prejudice. I was wondering, when you make this decoding of the human knowledge and you put in a robot, there is a chance that you may get this kind of human problems. I don't know. I just speculate and guessing. I don't know.
Well, like we said, that's the future, and we still don't know how things will develop. And we are working, and thousands of people are working in this area. And I show that the brain-inspired approach is now in more than 100 labs in the world. So I think we will see in the future what will happen, but it's a very exciting time.
Yes, so it seems that you still have a lot to learn, a lot to, because most of the problems we have today with artificial neural network you didn't know in the past. For example, the prejudice. Prejudice is something like, I don't know, people would be able to get that neural network would be able to incorporate. Because most of the artificial neural network stuff, you don't know. You know, you give the data, you expect the model to learn, but how it learns, all the mechanics, you cannot control very well. That's the idea of learning machine. Learning machine is the idea that they can learn by themselves. So, but there is this side effect that you don't know precisely what's learning. In this case of Brazil, in that bad name.
If the machine has a brain template in it, we can always copy what is in the machine. We can copy the connections and we can understand what the machine has learned. So I think that is the unification of learning between humans and machines that helps us. We are still in control. We can print out the brain of the machine. We can't do that for the human easily. And then we can understand what they learn. So I think this is one way to go in the future.
You said something in your book that I don't know if I understood properly because it stayed in my head. You said something in your book that I'm not sure if I understood properly. It seems that you'll be able to send the computer to make the calculation back take the calculation back. So imagine you have a very heavy calculation. Instead of you doing your brain, you communicate with the computer do the calculation, and the calculation come back. I got it right or it's wrong? I mean, is it right?
That's
I don't know.
quite an interesting idea. I think I have learned from you quite a lot today, by the way, and you always generate new ideas. I will take some ideas with me. Thank you.
So it's my pleasure. But I learned a lot of your book. I started to read your book. I thought to myself, that's a very boring book. But as I started to read, I could not stop because it's because artificial intelligence is beautiful because you can imagine how the future will be. But sometimes you get so caught up on the kind of application that you are unable sometimes to go to the future to imagine how that will be and what will be the kind of for example, I was watching an interview by a very famous Brazilian musician. He's famous all over the world, and he was talking about because in his mind, the artificial intelligence will always be slave of human because he was asked. Nowadays, computer can almost create music, like you saw in your slide, an example of classical music. But his mind, the artificial intelligence, will never be able to overcome human in terms of creativity. But I have some doubt. What are your thoughts about it? Because there is the limit. There is I don't forget the name. I forgot the name of the paradox. But the paradox say that what machine can do well, you can't. What you can, machine cannot do. But it's just a paradox. I mean, what about if you can break this paradox in the future?
Well,
Do you think it's possible?
This border is getting, it's very fuzzy border between what can machine do and what people can do. And it is always changing, I think, and it is more machines can do more, getting closer to humans in terms of decision making and perception and even we will see development in consciousness of machines. So the border is actually the gap is closing. The gap is closing.
Yeah, because I was reading the book of Kasparov. Kasparov, I don't know if you know him. He was a chess player. He was the first chess player to lose to a computer. He wrote the book. A year later, he said that now nothing right because he was very sad. He lost to a computer. But he was the first one that was it wasn't the dawn, the last stand of humankind. Like humankind, just the last he was the last stand, but he lost unfortunately to a computer. Nowadays, a single computer can beat several letters at once. In the past, it was the opposite, but it was so fast that he told he was scared how fast he lost. So as you said, the boundaries is getting very close and fast. You are like. Sometimes you cannot even predict.
And the future is actually shown in the poster behind you, which is symbiosis between humans and machines. That is exactly what we thought.
No, it was how
we can make
it. Inspired me. It was you because when I read your book, I supposed to have another poster, but when I read your book, I thought, wow, you are very close, because talk about the brain inspired artificial intelligence. It's more like this picture, like the brain, the human and the machine finally getting together in the brain, because you said like we can communicate with the computer, computer can communicate with us, so we're gonna have a kind of as you said, symbiosis. Using the word symbiosis. I think you used the word symbiosis, right?
Absolutely. So thank you.
Yeah.
You are a creative reader. You read the book and you generate ideas. And I like talking with you. We should talk again.
Yes, you are always invited to come to the channel. You're also invited to talk to me. I was always glad because all the time I talk to you, when I saw your course, I was inspired. I even tried to publish a paper, but unfortunately, it didn't go very well. The paper wasn't accepted. But anyway, I was very inspired. Yes.
Thank you for inviting me. Thank you for the audience. So it has been a pleasure.
So it's my pleasure. You're always welcome to come here. And guys, that's all. Talk about today about the spike in your artwork. In the description of the video, you're gonna have the slides. Professor Kasabov, I'm going to leave his LinkedIn profile, so you can go there and check out his work. And I'm pretty sure that you're always happy to answer questions in the future you have in. Okay, so see you in the next slide.
Thank you very much. See you again in the future. Thank you. All the best. Thank you.